Hi students, as a part of nanomaterials, today I am going to discuss very important synthetic method by which we can synthesize the nanoparticles. That particular very important synthetic method which is used to prepare the nanoparticles about which I am going to discuss today is physical vapor deposition method. Physical vapor deposition, which is abbreviated as PVD. So it is most familiarly known as PVD process of synthesizing the nanoparticles. Now let us see what exactly the PVD involves. This physical vapor deposition method involves the transferring of gross pieces from a target and depositing on the substrate. Transferring of gross pieces. Now what do you mean by gross pieces? Gross species is nothing but the species which is going to convert into the nanoparticles. The species which is going to convert into the nanoparticles during this particular physical vapor deposition method is called as gross pieces. Now this physical vapor deposition method involves the transferring of gross pieces from the target and depositing on the substrate. Now, based upon the source by which we can remove or eject the gross pieces from the target, this physical vapor deposition, usually called as PVD method, is being categorized into two groups. Right? So, based upon the source by which we can remove or eject the gross pieces from the target, this particular physical vapor deposition method can be categorized into two groups. The one group is evaporation. And the second group is sputtering. Now, based upon which criteria this categorization of physical vapor deposition has been done into two groups, based upon the source by which we can remove or eject the gross pieces from the target. Now, if the source of removing or ejecting the gross pieces from the target is heat, if it is heat, then physical vapor deposition is nothing but evaporation. On the other hand, if we use plasma, the plasma as the source of removing or ejecting the gross pieces from the target, then that particular group of physical vapor deposition is so called as sputtering. Right. Now, during this evaporation, which is one of the group of the physical vapor deposition, very low pressures are being maintained. Now let us see what is the range of that very low pressure which is being maintained during this one group of physical vapor deposition. That is evaporation. That is 10 to the power of minus 3 to 10 to the power of minus 10 torr. Let us come back to the evaporation later. Now let us talk something about the sputtering. Now the sputtering is utilizing the plasma. That is, it is utilizing the energetic ion or fast ion in order to remove or eject the gross pieces from the target. Now it is utilizing the energetic ion. So since it is utilizing the energetic ion in order to remove or eject the gross pieces from the target, this particular sputtering process is especially used to remove or eject the gross pieces from the target. From which target? From the high melting point materials such as ceramics and refractories. Ceramics and refractories, because in the case of sputtering we are going to use high energetic ion or fast ions. That is the reason it is especially used to remove or eject the gross pieces from the high melting point materials such as ceramics and refractories. Now let us get back to this evaporation. Now as the very low pressure is being maintained within the range of 10 to the power of minus 3 to 10 to the power of minus 10 torr, mean free path of the species is very large, right? As this particular evaporation, which is one group of this physical vapor deposition method, is utilizing the lowest pressure, which is in the range of 10 to the power of minus 3 to 10 to the power of minus 10 torr, mean free path of the species is very large. Since the mean free path of the species is very large, we will get low quality nanoparticles making use of this particular evaporation method, which is one group of physical vapor deposition. Now in order to get the high quality nanoparticles making use of the evaporation, the extension of this evaporation group of the physical vapor deposition has been done. That extension of this particular evaporation, which is one group of physical vapor deposition, is nothing but inert gas condensation. It's nothing but inert gas condensation, which can be abbreviated as IGC. Abbreviated as IGC, inert gas condensation. Now, what is the speciality of this inert gas condensation? In the inert gas condensation, we are going to use the inert gas in order to reduce the mean free path of the species. If we reduce the mean free path of the species, definitely whatever the nanoparticles which are going to be obtained will be highly pure when compared to the evaporation technique, in which mean free path of the species was very, very large. So high quality products are going to be produced. Why, students? Because in this inert gas condensation, we are going to use inert gases such as argon or helium, which reduces the mean free path of the species, by which instead of producing the low quality products, unlike the evaporation, we are going to get the high quality nanoparticles. I hope you got it till now, right? Now, this is the equipment which is required for carrying out the inert gas condensation, students, which is usually abbreviated as IGC, right? And this equipment name is ultra high vacuum chamber. Ultra high vacuum chamber is required for carrying out the inert gas condensation, which is the extension of the evaporation, which is one group among the evaporation and sputtering of the physical vapor deposition. Right? Ultra high vacuum chamber. Now, what we need to do is, so before that, this particular inert gas condensation is especially used to synthesize metal nanoparticles as well as metal oxide nanoparticles. Metal nanoparticles and metal oxide nanoparticles with the narrow particle sized distribution. With the narrow particle size distribution, that is, whatever the nanoparticles which are going to be produced during the inert gas condensation process will be in the range of 2 to 100 nanometers. Approximately 2 to 100 nanometers. 2 to 100 nanometers. Let us come back to our chamber. So, usually the metals are being taken, right? Now in this ultra high vacuum chamber, what we have to do is whatever the metal which is supposed to be converted into the nanoparticle should be entered or taken in this ultra high vacuum chamber. And at the same time we have to pass the inert gas, either argon or helium, which is, what is the purpose of this inert gas, students? Which is reducing the mean free path of the spaces. Right. Now these two are the evaporation boats. Now what do you mean by evaporation boats? Evaporation boat is the boat which heats the material to vaporize. Now under the influence of this evaporation boat, whatever the metal which has been entered into the ultra high vacuum chamber will vaporize. Now what are the substances which are present in this, students? Two substances are present. Vaporized metal particles and inert gas molecules. Now as this evaporation boat is supplying the heat, more and more number of vaporized metal particles are going to be produced. Now the concentration of vaporized metal compounds will be, metal particles is being increased. At the same time, the concentration of the inert gas molecules, either the helium or argon gas molecules, increases, due to which the collisions occur between the vaporized metal particles and inert gas molecules. So due to these collisions between vaporized metal particles and inert gas molecules, these vaporized metal particles will lose the energy. Now as collisions limit the mean free path, supersaturation is achieved. This concentration will be increased. The concentration of the vaporized nano, that is vaporized metallic particles is increased. That is, as collisions limit the mean free path, supersaturation is achieved above the vapor source. Just imagine. At high supersaturation, these vapors rapidly form large number of clusters. At high supersaturation, these vapors rapidly form large number of clusters. So, what happens is, these vaporized metal particles will move towards the cold finger. Now, what is the cold finger? cold finger is a device which is used to generate the localized cold surface. And this cold finger comprises the liquid nitrogen as the coolant. Under the influence of this liquid nitrogen as the coolant, cold finger is operated at a very low temperature. Now, all the hot vaporized metal particles will move towards the cold finger, and as they are hot, once they reaches the cold finger, which is cold, which is in the cold condition, these metal, that is vaporized metal particles, will deposit as the clusters. Will deposit as the clusters. Deposit as the clusters. Right. Now, what are these clusters, students? These clusters are the metallic nanoparticles. Metallic nanoclusters. Now, what is your next job? Nano clusters, nanoparticles have been formed. Now, we have to collect the nanoparticles or nanoclusters which have been deposited on the surface of the cold finger. Right? That job is done by the scraper. That job is done by the scraper. So this scraper will scrape the nanoclusters which are adhering or sticking to the cold finger, by which these nanoclusters are collected in the collection tray. This collection tray is being placed in high vacuum chamber. Why there is a need to place this collection tray in the high vacuum chamber? That should be the question. That should be the question. So this collection tray which is collecting the nanoclusters is placed in the high vacuum chamber in order to avoid the oxidation of resulting nanoparticles. So in order to avoid the oxidation of resulting nanoparticles, we have to maintain high vacuum conditions. That is the reason whatever the nanoparticles, whatever the nanoclusters which are going to be collected are collected in the collection tray which is being placed in the high vacuum chamber. Not only this, at the same time, we have to add the surfactant to the nanoclusters which are going to be formed, or nanoparticles which are going to be collected in the collection tray. So why the surfactant is being added? In order to avoid the agglomeration of the nanoparticles which are being produced. So what is agglomeration? Agglomeration is nothing but the merging of the particles. Once the nanoparticles which are formed merges again, they convert back to the bulk material. So there is no meaning for the process. So in order to avoid this agglomeration of the nanoparticles which are being collected in the collection tray, we have to add the surfactant immediately. So after that, this tray comprises the nanoparticles. So this is how we can prepare the high quality nanoparticles making use of inert gas condensation method, which is the physical vapor deposition method, and it is the extension of one group of physical vapor deposition method, which is the evaporation. Now, as each and every process will have pros and cons, that is advantages and disadvantages. Now let us see what are the advantages of this particular inert gas condensation method and what are the disadvantages of this particular inert gas condensation method. So advantages are high production rates approximately 60 grams per Planck constant. 60 gram per Planck constant. And high yield, approximately 75%. 75%. High purity of the final product, that is highly pure nanoparticles are going to be produced. Why highly pure nanoparticles are going to be produced? Already I have explained to you. Right. So highly pure final compounds with narrow particle sized distribution. Already I discussed that. Whatever the nanoparticles which are going to be produced during this inert gas condensation will be in the range of 200 nanometers. Next. So making use of this inert gas condensation, not only we can prepare the nanoparticles, we can prepare the metal nanoparticles, alloys, ceramics, intermetallic compounds, semiconductors we can prepare, composites we can prepare, so followed by so on. Right. Another advantage of this method is flexible technique and size can be controlled. So coming to the cons, that is disadvantages. So formation of the clusters and large size particles. This is the problem of this inert gas condensation. Huge amount of nano clusters are going to be formed. And if at perfect time we are not going to add the surfactant, these nano clusters immediately agglomerate and revert back to bulk. So very expensive due to ultra high vacuum chamber is being used in order to obtain the high quality material. And high purity raw target is utilized during this particular inert gas condensation. So low yield per batch, not suitable for synthesizing gallium arsenide and indium phosphide, because this gallium arsenide and indium phosphide are the semiconductors. These cannot be synthesized making use of this inert gas condensation because they easily decompose to the individual components under the conditions which are being maintained in the inert gas condensation process, which is the physical vapor deposition. I hope you understood this particular physical vapor deposition, students. Right? So, if the physical vapor deposition is being asked, so explain what is the physical vapor deposition and categorize into two groups, explain about the two groups. Then you have to write inert gas condensation, which is the easiest technique. Right? So actually, I got so many comments to do, so many requests to do the video on physical vapor deposition. I didn't find the good content to make the video on physical vapor deposition. So now I found the good content and I made the physical vapor deposition. I hope it is very clear to you. So thanks for watching, students.